Hello, my name is Franco, and I'm the author of Real-World Physics Problems. For this video, I'm going to be talking about how far a big wheel can roll on a flat horizontal surface. So there's an interesting problem that can be solved based on this analysis. But before getting into that, I'm just going to go through some basic physics here in order to set up the problem. So shown here is a wheel with a radius r, and the center of mass of the wheel is denoted by G. And since this is a uniform wheel, then the center of mass G corresponds with the geometric center of the wheel. And we wish to determine the distance d that the wheel rolls, which can be thought of as the distance that the center of mass moves in the horizontal direction. The other variables in this problem are omega 1, which is the initial uh, rotation rate of the wheel, and the point P is the effective contact point between the ground and the wheel, and Fp is the resultant force acting on the wheel at point P due to the contact between the wheel and ground. And point P is offset a small distance d from the center line as shown. As the wheel rolls on the flat horizontal surface, it slows down, so it experiences an angular acceleration alpha in the clockwise direction. And I use sign conventions as shown. And so alpha is the angular acceleration, and omega 1 is the angular velocity. So here the rotational inertia of the wheel about the center of mass G, treated as a two-dimensional problem, is given as beta times mr squared, where m is the mass of the wheel and beta is equal to some constant. So for example, for a uniform cylinder, beta would be equal to 1/2, and for a hoop, beta would be equal to 1. And alpha is equal to negative g times d divided by 1 plus beta times r squared. Now g here is the acceleration due to gravity, which is equal to 9.8 meters per second squared. Now the derivation for alpha can be looked at on this page here for rolling resistance, which is a page on my website. So if you go to my website called Real World Physics Problems and you search for rolling resistance, you'll find a page on that, and the derivation of the angular acceleration alpha is given on that page. I won't show that here because it's somewhat lengthy. Next, we say that d is equal to some constant times r. Now keep in mind that here I'm referring to small d, but the rolling distance I'm designating as large D. So I will just say small d when I refer to the lowercase d here. When I just say d, that means the rolling distance, which is the capital D. So small d is equal to c times r, where c is the coefficient of rolling resistance and r is the radius of the wheel. So if the radius of the wheel increases or decreases, the constant c stays the same. And once again, c is the coefficient of rolling resistance. So we substitute small d is equal to c times r into this equation for alpha, and we get alpha is equal to negative g times c divided by 1 plus beta times r. Now a, which is the linear acceleration of the center of mass of the wheel, designated by point G, is equal to negative alpha times r. And assumes that we have no rolling. This assumes we have rolling without slipping. So that's why we can write this expression here. And going back to this equation for alpha, A is equal to GC divided by 1 plus beta. So this is a positive quantity, so the wheel, as it slows down, is accelerating to the right, even though it's moving to the left. And similarly, v1, which is the initial linear velocity of the wheel at point G, is equal to negative omega 1 times r. So again, omega 1 is the initial angular velocity of the wheel. And we want to know the distance d, the rolling distance, and for that we have to know that at the completion of the rolling, that the velocity of point G is 0. So the linear velocity at the end of its motion is 0. So we just say v2 or v final is equal to 0. Now let's use a kinematic equation to solve for the rolling distance d, and we can use v2 squared is equal to v1 squared plus 2ad. So we just substitute in the values of v2 and v1, and we have 0 is equal to bracket negative omega 1r close bracket squared plus 2a, and a is the acceleration of point G. We substitute that in and we get 2gc over 1 plus beta times d. So we want to solve for the rolling distance d. And we have d is equal to negative 1 plus beta times omega 1 times r squared divided by 2gc. Now this is an interesting expression because it says that, for example, if a wheel is 10 times bigger, in other words, r is 10 times bigger, then it rolls 10 squared is equal to 100 times farther. So this assumes that the initial rate of spin of the wheel is the same, which also means that omega 1 is the same. So I can, for example, roll a tennis ball of diameter 6 centimeter, a distance of 2 meters, at an initial rotation rate of 2 revolutions per second. But if the tennis ball was 1 meter in diameter, using the same initial rotation rate, it would roll about 550 meters. So this assumes that the tennis ball is on the ground, and I roll it, and as soon as I release the ball, it's rotating at 2 revolutions per second. So a 6 centimeter diameter ball would roll 2 meters, and a 1 meter diameter ball would roll 550 meters. And that assumes that the initial rotation rate is the same for both, which in this case is 2 revolutions per second. So this highlights the significance of scale here, where r is a scaling factor, and the rolling distance increases in proportion to r squared, keeping everything else the same. Now for the interesting part of this video. So this large flywheel here was part of a large steam engine named Hazel, built by the Goldie and McCullough Company Limited in 1908, so more than 100 years ago. It is on display at the Waterloo Region Museum in Ontario, Canada. I was there, and it's quite a large wheel. It is 16 feet in diameter and probably has a weight between 8 and 10 tons, so it's quite heavy. This was used on a powerful steam engine of several hundred horsepower. So you needed this large, very heavy flywheel to enable the smooth rotation of the steam engine. Now the question becomes, if this flywheel ever came loose, how far would it roll? Now, so let's say that the flywheel is rotating at 100 RPM, which corresponds to omega 1 is equal to 10.5 radians per second. So 16 feet means that the radius r of the wheel is 2.44 meters, and we can use the coefficient of rolling resistance of 0.005, which roughly corresponds to the coefficient of rolling resistance for a steel wheel on asphalt. And g is equal to 9.8 meters per second squared, and beta is equal to 1. You remember that initially we said that Ig, which is the rotational inertia of the wheel about the center of mass g, is equal to beta times mr squared. For a flywheel such as this, it's approximately a hoop shape since most of the mass is distributed around the outside perimeter, so we can say that beta is approximately equal to 1, although not quite, but close enough. Now what happens is, if we assume that this flywheel comes loose during operation, what happens is it immediately starts sliding along the ground. So it starts sliding, and at the same time it starts moving with horizontal motion. And by the time it stops sliding, it has already lost half of its kinetic energy. And that is because of the sliding friction between the flywheel and ground. So when sliding stops and rolling begins, the angular velocity of the wheel, which is the new omega 1, is equal to 5.25 radians per second. So the angular velocity decreases by 1/2. And then once this happens, when sliding stops, then rolling without slipping begins, and we can use the previous equations to solve for the rolling distance. So now we can apply the rolling distance formula, which is d is equal to 1 plus beta times omega 1 times r squared divided by 2gc. So we have all the values, and we just substitute them in. Now here I'm using the absolute value of d. Before it had a negative sign in front, but that's because of the sign convention used when setting up that problem. So we can just take the absolute value. So we get that d is equal to 3,349 meters. So the rolling distance d is approximately equal to 3 kilometers. So it rolls quite a long distance. So this is the approximate distance that the flywheel would roll on a flat paved road if it ever came loose during operation. So now I'm going to show you a basic animation showing what would happen. So the flywheel, drawn here, comes loose during operation. So what happens is it is rotating while also sliding along the ground. So there's initial sliding, which results in half the kinetic energy being lost due to friction. So there's sliding, and then the wheel stops sliding, and it's simply uh, rolling without slipping. So it just keeps rolling as shown. Oops, let me go back. So let's show that again. So the flywheel comes off the steam engine, starts sliding, and then rolls, increases in speed until rolling without slipping occurs, at that point, it just keeps rolling for another 3 kilometers. Right, and that completes the video for this problem. Thanks for watching.